Hello, I'd like to discuss and demonstrate the interference and the diffraction of light. Here I have a couple of small openings and a bundle of light waves coming up here with parallel wavefronts, and each of these wavefronts will pass through each of these two openings. A given wave will pass through both openings at the same time. This part of the wave will pass through this opening, this part of the same wave will pass through this opening, and then those waves will spread out in such a way that we have regions of constructive interference where crest meets crest, crest meets crest, and this point will propagate from here to here to here to here, traveling in that direction, and cause some bright light to form on a screen over here in this position. In between we'll have crest meets trough, trough meets crest, crest meets trough, and we'll have no light going to this point right here, so that'll be a dark spot. And then we have another bright spot up here where crest, crest, crest meets crest, and so on up this way, and similarly up this way, and another one down here, and another one down here. So we have a series of bright beams of light corresponding to constructive interference. In between we have some dark regions corresponding to destructive interference. So we have a dark spot, bright spot, dark spot, bright, dark, bright, etc. Now, the spacing of these bright spots and the dark spots, that angle of spread depends on two variables. One variable is the wavelength of light. The other variable is the separation distance between the two openings. I'd like to demonstrate that by doing some more experimenting, this time using the overhead projector. To do that, I'm going to turn the lights down and go to the overhead projector and the screen here. Here I have a series of semicircles, and here I have an identical set of semicircles. I'm going to overlap these two and let these simulate those light waves coming through each of the two slits that we just previously talked about. So this would behave as if it were one slit sending out light waves, and the other slit here sending out light waves. And when we put the two together, then we have a pattern that looks something like this, so that we can see the points of constructive interference. And here's another line of constructive interference with destructive interference in between. So we have the bright beams of light corresponding to constructive interference, and the places in between corresponding to destructive interference or darkness. Now, as I change the separation distance between the two slits, watch what happens to that pattern. I'm going to first bring those two slits closer together. Maybe we can keep track here of the two tabs here, representing the location of each of those two simulated slits here on our overhead projector. And I'm going to try to bring those closer together, and notice that the pattern spreads out. So if the slits are brought closer together, the pattern spreads out. If the slits are separated, the pattern bunches up. Again, if they're brought closer together, the pattern spreads, and I'll have it spread to about the position that I have shown on the chalkboard. Now, just like changing the separation distance causes the pattern to spread, if we change the wavelength, the pattern will also change. And to get the greatest angle of spread, we want to bring the slits close together, and we want to go to a longer wavelength. So increasing the wavelength causes a spread, bringing the slits closer together causes a similar spread. So the spreading, or the angle of spread, the angle at which this travels off this way compared to the horizontal line, for example, the angle between these two lines increases as the wavelength increases, and increases as the separation distance decreases.